Yes. Hello, everyone. Welcome to MACSMIN 2025. It's a great pleasure to introduce Professor Marjorie Senechal, who will talk about Alan Mackay and the local theorem. Over to you, Marjorie.
Thank you, Vitaly. So that is my title, and I think he pronounces it Mackay. But I've heard it both ways, but I think it's Mackay. I'm going to call it Mackay today. So this is Alan Mackay and the local theorem, and I'm going to talk about possible connections between his work and that theorem. And most of what I'm saying is speculative, and I assume that many of you will have better answers than I do, or better questions than I do, and I look forward to making this into a discussion. It can continue over years. Doesn't have to be right this morning. I just wanted to raise questions here more than to answer them. So let's see if I can. There we go. So you all may have heard of Alan Mackay. I'm sure all of you have. He died this year, just very recently, at the age of 99. He was a very eminent crystallographer all of his career. He's known for thinking and working outside the box being the unit cell. And he turned the subject inside out, and we're going to talk about the possible influence on him of the mathematician B.N. Delone. So this is a picture of Alan that my husband took, and I think this was 2009. And he's in his study at his own home. He was a good friend of ours. And he was many, many things. He was, as I said, a crystallographer. He was an iconoclast. Any dogma was something to be shot down or to be chopped down if possible. Visionary because he saw things before other people did. He was an artist. I'll come to that at the very end if I have time. A very funny kind of artist. He was a poet. He published poetry. He did many other things too. And he was a fellow of the Royal Society. And this is one page. He traveled all over the world, and he had friends all over the world. And this is one page of his family, of the guest book that he and Sheila, his wife, had at their home. So all guests signed this when they came. I counted the number of pages. Their son, Robert, photographed that and sent me the pictures. And there are 114 pages in this guest book. I don't know how many others there are. And every one of them, the people are from all over the world. And you see here, this is somebody from... The names can be, Japanese, Chinese, but this person was in London, Yugoslavia, University of Beijing. Here's India. This is me. This is in Colorado, Moscow, Volga von Stein, and so on. And every page is like this. It's people from everywhere, and it's just wonderful. And I'll tell you just a little more biography of Alan. He was born in Wolverhampton, England in 1926, and he studied physics and chemistry at Trinity College, Oxford. And then he joined the Birkbeck crystallography laboratory of John J.D. Bernal. And there he stayed. And that was a very suitable place for him. And John Finney will be giving a talk, I think, next week about him in that laboratory. I'll give the particulars of that at the end of this talk. So be sure to attend that either by Zoom or in person if you can, because that's going to be a wonderful talk. So anyway, after Oxford, Alan joined the Birkbeck crystallography laboratory, and he got his PhD there in 1951. And he stayed there and worked with Bernal all the years following. And their work they influenced each other immensely. So I want to show you the box that he was thinking outside of. You all know this. This is the box that as it existed when he was born in 1926. So these pictures are all familiar. This is a beautiful display at the St. Petersburg Mining Institute of crystals, and their beautiful geometric forms led people to speculate for years on what was the why. And this is Aui's version of the crystal structure of boxes being stacked and piles finished off to approximate the crystal forms. And so this was in 1822, and you can see the various different shapes that are being formed here by stacking boxes, but he did not say what the boxes were, just that they were receptacles of something. And then in 100 years later, 110 years later, we have X-ray 90 years later, I mean, X-ray diffraction. It seemed to validate this that crystals, in fact, were lattices, lattice structures. And that showed how, and that one thing way you could tell would be that passing X-rays through them, they diffract and you get sharp bright spots showing the long range order. So sharp bright spots became identified with long range order, and long range order became identified with the lattice structure. And crystals were then, this is Brave's work, put into, categorized into 14 different lattice types. And these are the boxes and these were called unit cells. And the crystal structure was then thought to be essentially these being repeated by translation and finished off to make the crystal structure. So that was what the box looked like that Alan inherited intellectually. And the great mathematically inclined crystallographers of the past, before him, like Fedorov, others, had asked and answered such questions as, given a repeating pattern, what is its symmetry, or i.e. crystallographic group? So what is the group of symmetries that map it onto itself? What is the structure of a crystallographic group? And how many different crystallographic groups are there in each dimension? These were questions that were asked and they were answered. And this was thought to be the essence of mathematical crystallography, to get these questions straight, to formulate them, and to answer them. And that was what it was all about. This was 1924, 2 years just before Alan was born. This was essentially completed, this project, with Polya enumerating and illustrating the 17 plane symmetry groups. This is now classic. And the title that he had, which I don't know if you can see it on my screen, I can't, but it said the analogy of the three-dimensional crystallographic groups, of which there were 230, and those had already been enumerated by Schoenflies and Fedorov working together, I think in 1891. And there was also a theorem proved that in every dimension, these crystallographic groups have invariant translation subgroups. So they all are lattice-based here. And how that works, let's see if we can, there. So these are a few of the drawings from the previous slide. And I just put the dots on two of them just to show how this works, that these are related by translation. The dots themselves form a lattice, and then you have a unit cell that could be used to make the repeating pattern. And you can do this with any one of them, and then the symmetries of these cells are how the lattices were classified. And so this one is a little different than that. This one would have been hexagonal and so on, but you all know this, and this I just wanted to put it up on the screen. So and then, of course, the famous so-called crystallographic restriction, which is what symmetries, given that all crystals are point lattices, what symmetries can they have? And that's assuming that they all are point lattices. This is in 2 and 3 dimensions. This is now understood in all dimensions, but for these two were the most ones that people were working with. And so we can see that if you can easily have a lattice with 6-fold rotational symmetry about every single one of its points. So what I've drawn here, you could do for any one of them. And the rotation of 60 degrees maps this entire thing onto itself and the entire lattice onto itself. And 2-fold rotation does that, 3-fold, 4-fold. It's very nice. Missing here, you have 2, 3, 4, no 5. 5-fold doesn't work. If you try exactly the same thing here, there are many proofs of this, but I'm giving you this particular one. If you try this one here, you make a 72 degrees, but use these as the basis vectors for your lattice, you get the red points that I have. But then if you try rotating around this point 72 degrees, it doesn't map itself onto itself. So the lattice does not map onto itself. And 5-fold rotation is not possible for a lattice. And the similar argument works in 3 dimensions. And also not only 5-fold, but 7, 8, 9, 10. The only ones that do work are the 2, 3, 4, and 6. And this is called the crystallographic restriction. And that was just gospel. Anything 5-fold was impossible, or 7, 8, 9, 10, and so on. And it's this that Alan Mackay was questioning. Noticing this is from Howey's, this is Howey's picture. This is a pentagonal dodecahedron, but the pentagons are not regular. If they were, that would have implied some sort of 5-fold symmetry in the lattice structure that made this crystal. But this is not a regular pentagon. And everybody said, yeah, see, this just shows that the crystallographic restriction is actually correct. It doesn't even show up in the real crystals. So,
Marjorie,
yeah.
Can you hear us?
Yes. Can you hear me?
Yes, yes.
Okay, great. Marjorie, please continue.
Okay. So, but Alan Mackay was not working he was working in crystallography, but he was working in other things too, and he was in Bernal's lab, and he encountered fivefold symmetry all over the place. But these were in short range order, not long range order, but short range fivefold symmetries. And so this was something that he remarked in an interview with István Hargitai later. The icosahedron came up in several contexts. I knew about beta tungsten because the work he had been working at Phillips Laboratory has essentially icosahedral structure. That's not crystallographic there. Bernal was early to consider the icosahedral coordination because it would not crystallize is key to the structure of liquid and water, like liquids like water. So and they were studying liquids there intensively. And then the poliovirus, which was icosahedral particles, and people knew about that. So it wasn't that fivefold symmetry was forbidden. It was forbidden in crystals, but not in other things. And in that Bernal laboratory, they considered many different things. So this was very familiar for him. And then he published a work that made him very famous at the time. Alan, this is and which he presented what he called the Mackay, or what has been called by others the Mackay icosahedron. This was 1962. And again, István asked him about that later. What is it? And his answer, I'll read it, just icosahedral shells. Bernal was extremely keen on hierarchy as a principle of building things and generalizing crystallography. And when there was the discussion related to polio and so on, he asked, what happens if you take 13 atoms to make an icosahedron like this? So there's a central one, and then 12 surrounding it in icosahedral formation. And then you take 13 of these and make a bigger one, and then 13 of those and make a bigger one still. And he said that's now known as a fractal. So this was a discussion that was going on in the Bernal lab. And then Alan realized that you can see that these they just become like bigger and bigger icosahedra. It's still on the very small finite scale, but bigger, larger and larger. And each face looks like a cubic close packing. And it does actually grow out as he says, as twins of 20 ordinary face-centered cubic packed crystals. So as if you took 20 face-centered cubic packed crystals and sucked them together, you might get something like this. Or you can start with this and grow out by adding shells and shells and shells, and this is what you get. And this would be taken out 3 or 4 shells, not a lot. After too many, it became unstable. But in many contexts, this thing was very insightful. And so I Googled it to see what AI would have to say about it today, or rather yesterday. And it said, the Mackay icosahedron is more than just a theoretical curiosity. It describes the structure of real-world materials at the nanoscale. So this is how it's seen by AI today. Nanoparticles, common structural motif in gold nanoparticles, clusters of other metals such as palladium and rhodium, alloys and quasicrystals. Of course, Alan didn't know about quasicrystals. That was much earlier, but now you could say it that way. The 55 atom Mackay icosahedron, I think that's 2 shells, has been proposed as a structural unit in intermetallic compounds and the aperiodic lattices of quasicrystals. Colloidal aggregates provides a model for how colloidal particles can assemble into larger ordered structures, and viruses, which I just was mentioning. So there are lots of things. And then they carefully mention AI responses may include mistakes. Learn more. So I think these things are all correct, but there may be more to say about it. So this is, and Alan is still known for the Mackay icosahedron. And then István, as you know, has interviewed many scientists, and he interviewed Alan a lot. And those are extremely helpful now to look back and see what they were talking about, and what they were thinking about. And here's another one of his interviews with Alan. He prefaced it by saying Alan questioned dogmas wherever and whenever he met them. The approach to discussing crystal symmetry used to be to think about the formation of a crystal as through insertion of individual atoms or groups of atoms into the 3-dimensional framework of symmetry elements. In other words, you have a picture like those that Polya drew, and then you put the different atoms in there so that the framework existed and you put the atoms in. Whereas in reality, as Alan liked to point out, the symmetry elements emerge as a consequence of the structure being formed through the local interactions between individual atoms or other building elements. So it starts out with a random group which self-assemble into local groups, which assemble into larger groups, rather than the picked structure being there waiting for these to be the atoms to be stuck into it. And this brings us to Delone. And here's a picture of him. And he's looking like he's in a mountain climbing suit. And the reason he is that he often was in a mountain climbing suit, and he climbed mountains all over. And there's even a peak named for him in the I forgot which mountain group it's in, but anyway, it's called Peak Delone. You can Google that, and it's named for him because of his wonderful climbing abilities all his life. He did a lot of wonderful things, and he was a mathematician of great renown, particularly in number theory. He was in St. Petersburg most of his career, but we're going to talk about what are called Delone sets, which were not part of number theory, but they were the thing that revolutionized, I think, mathematical crystallography, took it out of the box. That began with several earlier papers, but most famously with his book here, The Mathematical Basis of the Structural Analysis of Crystals, in which he introduced what he called Delone sets, or he called them RR systems. We'll look at those in just a moment. And this is 1934. He and Pedurov and Alexandrov together. And it also brings it describes the, excuse me, the X-ray crystallography and the whatever was known at the time about being able to understand the structural analysis of crystals. So there is him. Unfortunately, I never met him. I wish I had. I was in Moscow in a year when I could have met him, but I didn't know that at that time. I did meet his students, and I'm still in touch with them. Just to clarify, if there's any confusion, this is one transliteration of the Russian way of writing Delone. It's also transliterated as Delone this way, the French. And this may be the way that the family name originated. It's thought that one of his grandfathers, somebody came to Russia with Napoleon and stayed, and that was a Delone related to the Delone artist. So it's an interesting family. But then there's another one named Delaney, and that is not Delone, and that's not this Delone either. It's another person. Okay, so there's a picture of Boris Nikolaevich, and he was born in St. Petersburg in 1890, and he was gifted in music as art as well as in mathematics. And his students and colleagues thought that may explain his gift, especially in art, his strong visual sense of crystallography. So for him, these weren't theoretical constructs, they were visual constructs and as well. And that may have been connected to his interest in giftedness in art. He studied at Kiev University, he taught at the Steklov Institute and Moscow University, and he taught at Steklov before it moved to Moscow and then after. He was renowned, as I said, in number theory, mathematical crystallography, and mountaineering. And interestingly enough, Voronoi was a friend of his father. His father, a professor of mechanics. His students have raised the question of, did Voronoi influence Delone, Boris Nikolaevich? And they think not, because the age difference was too great. And Voronoi died just as Delone was going to college. But he did know him. He met him in his home, and whether that matter or doesn't matter, I mean, if it influenced him or doesn't, we don't know. But it's just an interesting fact. By the way, all these numbers I have at the end, I have a list of all the sources, all the things I'm saying. So what are Delone sets? Or he called them RR systems, where there are two parameters, little r and big R. The little r is the minimum distance between any 2 points of the set. So these are discrete point sets we'll just say R3, it doesn't matter whether R2, 3, 4, 5, which have a minimum distance between points. No two can be closer than that. And they also have a maximum radius for an empty hole. So in particular, a good example is the sets of points of a Delone set cannot lie all on one side of a plane, of a bisecting plane. They're all over the place. It's homogeneous in the sense that no hole's bigger than this radius R. So here you have, this is not a point of the set. The red ones are the point of the set. Here's a hole, radius capital R, and there are 3 points on it. There have to be at least one in it or on it to be a Delone set. And this goes in all directions. So the minimum distance, little r between points of the set, and maximum radius of the spheres containing no points of the set. And as I said, he called them RR systems, and then since then they've been called Delone sets.
Marjorie,
Yeah.
does it make to clarify that such a set, due to the second condition, should be infinite?
Yes.
since your picture shows only a finite number of points.
Right, it has to be infinite. Yeah, yeah. Thank you for pointing that out. Yeah, yeah. Because of course I couldn't draw it being infinite, but I meant this goes on and on. It has to. Yeah. And one thing that this does that I didn't have time to make a slide of to show you is that when a set like this can be thought of in two ways. One is the point set, as I've shown it here, something like this. The other is the Voronoi-Dirichlet sets cells that go with it. So each point occupies a certain region of its own, which you calculate by drawing lines to all the other points and then bisecting those, and then the smallest polyhedron containing the point is the Voronoi cell or Dirichlet, that both names work. So this can be thought of as a partition of space as well as a distribution of points in it. And this is saying that there's a bounds on the minimum size and maximum size of these cells, but they can all be very different from each other, but this is a way of visualizing the distribution of the points in the space. And let's see now, how are we doing on time? Yeah, okay. So one of the things that he did, he reclassified the lattices in R3 by those cells, by Dirichlet Voronoi domains, instead of by unit cells. So he looked at and there he got some interesting results. So instead of 14 Bravais lattices, he got, I think, 24, because the parameters in each one of these sets varied, and the Voronoi cells can vary in their shapes depending within a single framework. And so this is one of his early pictures showing how that can be done. I won't go into details. I just want to show you that this was considered very important at the time. I'd like to understand better what people made of it and why and how, but they did that to look at the structure of crystals in terms of these cells rather than of the unit cells. And this drawing has the unit cells here, but now then, see, this is the same unit cell, and yet they have different Voronoi cells, and this was a deeper distinctions between them, which people were taken seriously, and I don't really fully understand what was done with it, but I'd like to know. So if you can tell me. So later, Delone and his students proved what they call the local theorem, which is that local regularity implies global regularity. So here let me get this structure of the theorem out for you first. I didn't realize this was animated. So this is they considered in a Delone set, every point has associated with it a star or a hedgehog, which is all the lines connecting it to all the other points in the set. And the local theorem says that in every system, there is some constant such that if all the stars of radius of that constant are congruent, then this is a regular system of points. In other words, it can map onto itself by its symmetries. And so this is a way of stating that the local symmetries imply the global symmetries. If you have local symmetries around every point, this example doesn't work for that, but if you had same sort of little stars at every point up to sufficiently large radius, then the entire thing is a regular system of points, and that is it's invariant under its symmetries. And this was the goal that Delone had in the first place. He wanted to show that with looking at the RR systems or the Delone systems, that they in fact do imply the formal structure of the regular systems of points or the symmetry groups, but they come from the local structure rather than being imposed by the global symmetry itself. And that's called the local theorem. And so this took a while for them to prove it. It was proved in 1976, but they had been working toward that for 30 years. And so that's called the local theorem. And this is what struck me and why I wanted to talk about this a little bit. Coincidentally, maybe, or maybe not coincidentally, how much connection was there between the groups like Bernal's group and groups like Delone? Delone's group in Russia, Bernal's group in England, but all of them were well-traveled people. All of them knew a lot, read several languages, spoke languages. In 1962, Bernal proposed a geometry of liquids, which, again, I had mentioned earlier that Alan Mackay knew all about the geometry of liquids because he worked with Bernal. Proposed a geometry of liquids based on atoms in empty space. That already sounds like a Delone set. That was consistent with a number of axioms, of which two of them were these: impenetrability, The structure is determined by the forms of the repulsive forces between close molecules. That's a little r. And homogeneity, that it's all over the place. It's not in any, they're not arbitrarily large holes. That's the big R. This is really very similar, isn't it, to the RR systems, to the Delone sets. Did Bernal know about those? I don't know. I mean, but there were connections between the groups, and I'd like to understand them better. And the reason I know that there were is that Alan gave me that book, that very book written by Delone and Padurov and Alexandrov, his copy of it. He had a copy because Boris Weinstein had given it to him. Weinstein was the director of the Crystallography Institute in Moscow, and he gave it to his own copy to Alan just before he died, actually. And then many years later, 2017, Alan gave it to me. And I was deeply touched that I should receive this book, and I have it here right in this room with me. Let me show it to you. Oops. I don't know if you can see it. But anyway, here it is. This is a wonderful book. And the thing that's interesting here that Alan wrote in small, very small writing here, he said, I spent an evening with Delone in 1962, ALM. So we know they knew each other. 1962 was the very year that Bernal was working on the structure of liquids, and Delone and his students were already working on the local theorem, and there were many things were happening in 1962. That's when Alan Mackay published his Mackay Icosahedron. It was a lively year in this field, and they spent an evening together, and I would love to know what they were talking about. This, I don't think they would be spent the whole evening talking about the weather or mountain climbing. It would be interesting to know how much they shared, how much they influenced each other. I think that's a wonderful historical problem to be studied. So
Marjorie, do you
yes,
think they met? Sorry, do you think they met in Moscow?
yes, they did. Yeah, I can be sure they did. I'm not sure, but I know that I meant to mention it that year. Mackay spent, I think, 7 months or something in Moscow. So it's
Okay,
very likely that's where it was,
thank you.
because he was there for 7 months and at the Institute of Crystallography. So I
Mhm.
should have put that in. I'm sorry. And here I should have crossed out this extra A. I'm sorry about that too. But it was soon after that, 1975, that Alan was talking about generalized crystallography. And this is another of the things for which he's very famous, is this saying, essentially, forget the unit cell. Crystallography, these are some quotes from his first paper on generalized crystallography. He wrote about this year after year. Crystallography is only incidentally concerned with crystals. It's rapidly becoming the science of structure. The science of structure deals with form and function, particularly the way in which large-scale form is the expression of local force, which is what we've just been talking about. And that's where the local theorem comes in. I made the italics on mine here. And then he said, I think crystallography in general has not really come to terms with the problem of local symmetry. I'm not sure quite what he meant, but I think he may have meant that it hasn't yet, by the problem of local symmetry, how it influences the global symmetry. I think he meant that still this was up in the air. Of course, that was just about the time the local theorem was published. Now, these are two pictures that changed the world, at least the crystallographic world. This here, Alan has his son Bob. His son Bob was as a youth, was fascinated by computers, and he managed to plot a recursive pentagonal pattern, starting with a pentagon and then dividing it into subpentagons and dividing them into subpentagons and so on and so on and so on. And he heard, Bob and Alan both heard that Roger Penrose was working on something like that too. And they took this over to him and showed it to him, and then everybody was happy. And then Roger Penrose signed this. And then down here, Bob has written, was this 1975? Just to be sure what year it was, I don't think he remembers exactly which. But anyway, this, if you could look at this closer and closer, this is a hierarchical structure of the type that they were working on in Bernal's lab, and the type that, Alan got the idea of checking to see what would happen with an optical diffraction pattern of this. What would it look like? The long range, what kind of long range order might show up with diffraction or nothing? I mean, he didn't have any idea. He had a friend, who could do such experiments, and he sent this over there. And they made a pattern of the dots, which were the vertices, and did optical diffraction and got this. And his friend wrote to Alan and said, "I'm sorry, my machine is broken." And Alan said, "What do you mean your machine is broken?" He said, "Well, I got tenfold symmetry and it can't do that. It's impossible." And he said, "Well, wait a minute, let's see what's really impossible." And so this began the questioning of the crystallographic restriction. And it's true that lattices can't have fivefold, tenfold symmetry, but it's not true that nothing with long range order can't have that. So there are other kinds of long range order, and this is exactly what Bob Mackay was drawing with his was a hierarchical long range order, and we all now today understand that. But at the time they were stunned to think that they could get a crystal looking diffraction pattern, sharp bright spots, but this was clearly not translational order. This was a hierarchical order. And Alan presented this in 1981 to the International Crystallography Congress in Ottawa, Canada. And that was the first presentation of a pattern of tenfold diffraction symmetry, and people were stunned. I was in the audience at the time, and so were a lot of my Soviet colleagues. I had spent the 2 years before there, as I mentioned. Everybody was stunned by this. But nobody of that group foresaw that this would turn out that there were real crystals or real substances which would show the same thing. And so that is what happened. Next was Dan Sheckman the very next year, got his aluminium manganese diffraction patterns of tenfold symmetry, just like that, that Alan had. And he too said this can't be, this is impossible, but many years later he got the Nobel Prize for it. And this leads to another area, which I'm not going to get into, but people have debated this ever since, is whether Alan Mackay should have shared in that prize, because he was the first to present that diffraction pattern and to show that how it was made and why it was made, and to really break down the barriers of the unit cell and to turn the whole subject inside out. And then he continued to write about generalized crystallography. This is now 2002, so that's 27 years after the first article on it. The emphasis on infinite periodicity is somewhat distorted the development of crystallography. Development could have taken another emphasis, namely the ways space-filling polyhedra packed together. And that's what Delone had shown with looking at the Voronoi cells instead of just the unit cells for lattices. This approach pioneered by Delone. So by this time, he's actually mentioning Delone in his work, whereas earlier he had the similar ideas, but he didn't cite Delone or anybody else, just what was going on in Bernal's lab. And that's why I'm interested in the interactions there. But he says this approach, pioneered by Delone, asked about local order, developing a theory that asked out to what range are identical points required to have identical surroundings that generate crystallography, rather than given an infinite repeating structure acting under what operations is this whole object invariant. And then he said this Delone's approach is more suitable for a unified theory of crystals, quasi-crystal. This is 2002 now. Quasi-crystal hierarchical amorphous or statistically ordered materials. And so so Alan essentially for the rest of his life was interested in generalizing crystallography, but there were more and more things, more and more well-known objects to include in that and theories to include in it. Now, one of the things that Alan did, I'm coming at the end now, among many things he did, he collected scientific quotations and compiled 2 large volumes. One was called The Harvest of a Quiet Eye, and the other, I think, just was a dictionary of scientific quotations. And he's got wonderful stuff in there. And I went through them after he died and looked for ones that I thought were particularly apt. And I published some of those in the Mathematical Intelligencer that just came out as a list of more of these quotations. But these are 5 that I think are particularly apt for this talk and for understanding connections with the Bernal group and Delone. So I'll just read them out. These 5 out of hundreds. It isn't that they can't see the solution, it's that they can't see the problem. And I think this is there's more to this. The more you think about it, the more you see. Here's another one. Don't bite my finger. Look where it's pointing. Warren McCulloch. Warren McCulloch was one of the first to discuss neural networks. And he's now considered to be a pioneer in all of that area of neuroscience. I knew him too. He was a friend of my father's. It says, here's another one I love. I have yet to see any problem, however complicated, which when you look at it in the right way, did not become still more complicated. And then the purpose of models is not to fit the data, but to sharpen the questions. And then the last one out of this little group that I've chosen, the outcome of any serious research can only be to make questions grow where make two questions grow when we're only one grew before. And I think these all summarize his attitude, Alan's attitude toward science and toward the work that he was doing. And it gives us all things to think about and directions to go. So I think they leaves us with new problems, of which there are many, but I just mentioned a few. One is that fascinates me right now is tracing the interactions and mutual emphasis of these sciences and mathematicians. And how well did they know each other, and what did they share, and what did they get from each other? And the little bit that I've been able to turn up that I showed you makes me think there must be more, and I'd love to know more about it. Another is to take up Alan's challenge to use Delone sets to create a unified theory of crystals, quasi-crystal, hierarchic, and amorphous or statistically ordered materials. Actually use them and put them in, make them the basis of what we teach. And then another thing would be very interesting would be to compile a biography of Alan. He was in all over the world, as I showed you, knew people everywhere, went everywhere. He was very interested in Asia. He read and spoke several Asian languages. He was amazing. And I think that a biography of him would be quite something. Now, what would it be? It wouldn't be an ordinary biography. I think it should be more like what he wrote himself. He compiled, toward the end of his life, he compiled all his, not all, but many of his writings into a huge volume, which I also have over here, but I won't waste your time to go look for it. But a huge volume that he self-published. And in here are many, many of his papers of all different kinds. And it's a fascinating thing just to prowl through. A biography could be that too. It could have many, many writings. Istvan Harkatay has organized over the years 2 special issues of his journal, Structural Chemistry, devoted to Alan for his 90th birthday and I guess for his 95th birthday, whatever. And there's another one going to be coming out soon in memorial to him. And those things, plus many other things about him, would make a wonderful collection to call a biography. And I just want to end with showing you this picture here, which is the collection that he made of his own. He called it Eclectica. And I think that's a great title for it. But what do you have here? This is a picture. This is a minimal surface that he had studied. And I don't know if he generated, I don't know how he got the picture, but anyway, it was one that interested him. A triply periodic minimal surface here. And what it looks like is a sculpture in a big courtyard. And he claims actually that this is at the University of Mexico, this big sculpture. And you see somebody walking behind it, and you see the building over here, and it's quite a sculpture, except that it's not a sculpture. He faked this. This is like Greg's picture in the background with the planets, and the university does not have any such sculpture. He just put this in front of it. He not only did that, he made up an artist named Sho Takahashi, who he claims were the sculptor of this thing. And he even had exhibits at conferences of Takahashi's work. And all of these were minimal surfaces that he had generated on some computer or something, and then taken background pictures from all around the world and stuck them in the courtyard. And he even had a little biography of Takahashi, and the whole thing was made up. And I didn't know that until just recently from his son Bob that was a pseudonym. I think that is a delightful touch of Alan, and I think that it would be fun to do a biography that honored him in that same way. And so then finally, in conclusion, just want to remind you the Bernal Lecture of 2025 will be John Finney speaking on September 23rd, just a few days from now. And he's going to be speaking on the harvest of an eclectic mind, that Alan Mackay and the rewriting of the book of crystallography. So I encourage everybody to attend that, and I will too, and I hope to learn a lot from it, and I look forward to that. And so I want to thank Istvan and Bob and my husband Sanchir, the photographer, for their help with this. And these are the sources that I have used, plus a few more that I may have forgotten to put in, but they're basically, I've tried to document this. And anyway, you can see this on screen. You don't need to see it right this minute, but That's it. So click to exit.
Marjorie, please keep your slides.
Oh, okay.
Yes.
I don't
Let
want
us
to.
first thank Marjorie for the beautiful presentation.
This.
Yes, physically or virtually. And now I'll stop